All right, so just after last class, somebody was talking to me about formulas versus circuits. And I think it's worth spending a minute on it. All right, so this is a circuit, right? You have variables at the top, which are true or false. And then you have AND gates, which take in this case, the fan in is 2, right? So each takes in 2 values. And this will output is x1 and x2 true, right? And then you take the outputs of these gates and you feed them into OR gates and NOT gates. Everybody get these things? Right? So that's so there's the values, and the values can percolate down. And there are actually lots of gates you could have, right, which have 2 inputs and 1 output. But it turns out you can prove that for any function, you can compute it with AND or and NOT. All right. Okay. So all right. So all right. So here, this is just saying, for example, suppose you wanted to compute P exclusive OR Q, right? Then one way of computing it is saying, well, remember what this means. This means one of them is true. Exactly one of them is true, right? It's exclusive OR. So one of them is true, but they're not both true, right? So here we can say, well, when is that the case? Well, when P is true and Q is not true, then it's true. And it's also true when P is not true and Q is true. And it's true in both of these cases, so that we put an OR between them. Right? Does that make sense? All right, so there's a little circuit that computes it, right? So if you had a circuit that had a parity gate, you could replace the parity gate with an AND or NOT circuit, right? And there, all right, so here we do it on these variables, and then we do it on those variables. And now what happens if we want to put a parity between them, right? Well, so a circuit, the advantage of a circuit is once you've computed something, right, you can reuse the value again, right? Because you can have these, in contrast, we're going to see in contrast the formulas. What we've been looking at before have been formulas, so you can't automatically reuse them. So here you'll see the value of this is fed into these alpha places, and the value of this are fed into these beta places, and we get a compute. Right? Does that make sense? Now, in contrast, a formula, something that you write down in one line with AND or NOT and brackets, right? You can't reuse things, right? So if you wanted to write it down as a formula, you have to compute it twice, right? And so that makes the size of the thing grow exponentially, right? So there certainly are functions that can be computed by small circuits, but if you try to change them into a formula, then they grow exponentially big, right? Exponential in the number of variables, right? Does that make sense? Right, so in this case, it's not growing exponentially big. It's only growing to be of size n squared, which you can do the math if you want, but it's still pretty good. All right, so there's this idea of reusing happens other places. Like if you're writing code, you can write some code, and then you can use it many times, right? And in fact, better than that, you can take the same code and make, this is assuming that we're sorting an array of integers, right? But you could have generic code where you're just saying, I'm sorting an array of objects, and you can reuse this algorithm. All you have to do is plug in different types and different, and when it comes down to it, you have to have different comparisons, right? You're sorting elephants, then for any two elephants, you have to say which one's bigger, right? So you need different, right? So similarly with proofs, right? So somebody proves all of these using maybe the Davis-Putnam method. We prove them all. And then you can use them as many times as you want, right? So we could start with a small proof system and then prove all of these things, and then you can use those as much as you want. And it just, I've done some of the work for you by writing down some useful, these, we call them lemmas. Everybody good with that? Right, and when we reuse them, right, here is all alphas and betas, but you can here's what's the difference between when I say sort of capital P and when I say alpha is P is thought to be a variable, right? An atomic, it's true or false. And here my alphas represent any big complicated structure sentence, right? So you have some sentence alpha and you have some sentence beta, and you've proven alpha and you've proven alpha implies beta, right? All right, and circuits, yeah.
Statement.
Yeah, so alpha will be some sentence in logic, and beta will be some sentence in logic, and right. In fact, what we're going to do next is we're going to expand what a statement is. We're going to bring in fralls and exist, right? And all of these are true even then, right? If alpha, all you need about alpha is that it's some big thing that in your universe either evaluates to true or it evaluates to false.
The variable is like it could be a true or.
Yeah, a variable is just your simplest, just one variable, one statement. The sky is blue is kind of a variable, right? It's either true or not. All right, so circuits obviously reuse things. All right, so now I'm going to just for fun, again, don't complain about this, but I didn't learn this until grad school, but I think it's useful to know. All right, so we're going to take any function and we're going to compute it with the circuit. All right, so what is a function? Well, if there we have 6 variables, right? So 6 inputs, and when the input is all zeros, then our required output is 0, right? And so this is just the table of size 2 to the 6 that lists for every possible input what you need your output to be, right? And now we're going to try to design a circuit that computes it. And ideally, they're nice small circuits that compute it, but we're not going to try to go there. We're just trying to say, I can always build some circuit to compute it, right? So, right, that's just our sizes there, and we're going to build some circuit. All right, and our circuit's going to be big because it's going to basically be a table lookup, right? So what you're going to do is take any input that gives you a 1, right? And we're going to build a big and this big and basically says it returns a 1 if and only if that's the input, right? So you can see here it says x1 is 0, x2 is 0, x3 is 0, so forth, right? In this case, the last x in, oh, you see I don't have a negation on the last x in because it's not, right? Everybody see that that's what it does, right? So that's what I said it does, and then we do it for the next one, and we do this for every one in the table, right? And then what do we put between these? Yeah, we put a big OR, right? And now this circuit is going to compute our function. Why? Because if the input is supposed to be a 1, then one of these ands is going to say, yes, that's our input. And then the OR is going to say 1, right? And if the input's not one of these ones, then all of these ands, each and is going to say, nope, that's not my input, right? And then the OR will say no, right? Does that make sense? All right, so then you've all taken 2001. Have you all taken 2001? Maybe. No, maybe you haven't. But anyway, you're going to learn about Turing machines, right? And Turing machine, you have this tape and you have this state and you do state transitions. And given any Turing machine, we can build a circuit that computes the same thing, right? So across here, I'm going to have just a lot of wires, right? So for that, each of those 0, 1s, there's a wire which says, is that bit 0 or 1 on my, right? This is my current tape. I have values on my tape, and this wire is going to say, I have a 1 on my tape cell. I have a 0 on my tape cell, right? And here I block those tape cells, those tapes together to say, hey, this in binary is the letter H, right? So here I'm saying hello on my tape, right? And here's a few more wires in my circuit, which tells me which state I'm in. And I have this next to the H because that's the head moves. And so here, if the head was here, then this would be telling me where the state is. But the head's here, so this tells me where the state is, right? For what it's worth. And then this is encoding, right, the state of the machine at one point in time, right? And if you're trying to encode some other machine, you have your machine, and this is just a bunch of wires, and the wires encode what's the state of your machine, right? And then down here we have, well, what's the state of your machine? If this is the state of your machine at time t, because it's tth level in my circuit, right? Then t plus 1 level of my circuit will encode what's true at time t plus 1, right? And then we just have to bang in some little circuits to get you from one to the other, right? Does that make sense? And so then how big is the circuit? Well, the width will be kind of how much memory, how much bits do you need to store your state. And the height of this will basically be what's the running time of your Turing machine. Right? Does that make sense? So if your Turing machine runs in polytime, then we can build a circuit in polytime. All right.